Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Welcome to lecture 5 of module 1, where we are trying to give you introduction to the course, basic concepts and physical principles and process applications in brief. In the first 3 lectures, we have given you units and some concepts behind vacuum like mean free path, time to form monolayer, etc. And in the 4th lecture, we try to utilize the physical concepts behind medium and low vacuum applications involving force and oxidation problems and boiling point reduction, etc. But today's lecture, we will try to go for high-tech applications. High-tech in the sense they require ultra-high vacuum and high vacuum. High vacuum means below 10 power minus 3 millibar to 10 power minus 6 to minus 7. There is nothing very strict definition of high or ultra high, there is a overlap. For example, medium vacuum ends at 10 power minus 3, but actually 10 power minus 2 onwards some ultra high vacuum concepts will come. And at the end of the high vacuum at 10 power minus 6 star, ultra high vacuum concepts take over. What is it that is changing when you go for low to medium, medium to high, high to ultra high? The mechanical force, which is P2 minus P1, stops almost by you come to 1 millibar, then 1000 to 1000 minus 1 is 999, 1000 minus not 1, 10 power minus 8 star also, it is also 999.99. You won't gain any extra advantage if your application is mechanical force. Similarly, drying or moisture removal, etc., because by 40 tar we are anyway coming to the room temperature boiling, or if you want to do freeze drying, maybe 1 millibar. Afterwards, you do not gain much. But very specialized applications like cryogenic freeze drying, etc., at very high vacuums, you have to maintain low temperature. That is a different special issue. So, most of the time medium vacuum is good enough for thermal applications, mechanical applications, suction applications, drying applications, etc. For chemical, pharmaceutical, force applications, filtrations, for example, in a chemical industry to accelerate the speed of filtration, the receptacle side, if you try to put vacuum, then the filtration speed will increase. I did not tell in the last class, but that is also one application, and it is going to save enormous amount of time in process industries, in chemical and pharmaceutical industries. Instead of 5 hours filtration, it may be 1 hour, then it saves a lot of money, and that saving compared to the vacuum technology cost of a rotary pump or something, it is hardly anything. Okay. Today, we will try to confine ourselves to high tech applications involving high vacuum and ultra high vacuum. In the last class, we have seen low vacuum and medium vacuum. So, today our story starts from 10 power minus 3 millibar onwards. As I told you several times, already 99.999% has been removed. Where is 1000 millibar, where is 10 power minus 3? 6 orders of vacuum we have already improved, but no metallurgy application, no electronics application, no space technology application, no nuclear application, no tube applications, X-ray tubes. So, most of the high tech have not started. That is because most of the concepts associated with the ratio of vacuum, not the difference in vacuum, they require better and better vacuum, like nuclear particle accelerators. If you try to improve one more order, it is going to reduce the scattering very high, so that your particle acceleration will be much more. Similarly, X-ray tubes, if you are having instead of 10 power minus 7 torr sealed tube, you have 10 power minus 8 torr, its life will be much more. Vacuum interrupters, instead of minus 7, minus 8 torr, then at very high currents when it is opening, even then no damage will take place. So, better the vacuum, it is always better. Metallurgical, metal coatings, engineering coatings, better the background vacuum, then during the actual evaporation, the background impurities are less to that effect. So, you will get a quality level. Similarly, semiconductor processing or semiconductor circuits, chip manufacturing, etc. Better the initial base vacuum, the quality of the chip will be better and better. So, keep this in mind as also a physical concept involved in it. Why we have to go for high and ultra high? Okay. When it comes to concepts involved in high and ultra high, we will not be using much about force or drying or thermal aspects, but electrical insulation definitely we will be touching upon, and low molecular density physical concept is very useful in high vacuum, ultra high vacuum. Associated with low molecular density, long mean free path comes into picture. We discussed in our second class or third class maybe, where molecular density, time to form monolayer and long mean free path, these are all interrelated. As pressure goes down, molecular density goes down, mean free path increases, time to form monolayer will be longer and longer, it will be cleaner and cleaner vacuums. So, you can start exploring to different high tech applications. Okay. So, these high and ultra high vacuum applications starting from 10 power minus 3 to 10 power minus 11 millibar on earth, because we cannot go beyond that, because even the chambers will start degassing. Otherwise, it will be better if you go to 10 power minus infinity, which is 0 millibar, that means absence of everything. That is impossible on earth. But in space, deep space, there is absolutely no matter, no gas, no liquid, no solid, nothing. Such situations are there, and if in future better and better vacuum pumps will come, better and better measuring technologies will come, control systems will come, chambers will come to really simulate those space conditions and to go to ultra high vacuum. Okay. That is very important in nuclear applications also. But right now, let us try to focus on 10 power minus 3 to 10 power minus 11 when it comes to high and ultra high. When it comes to low and medium, 1000 millibar to 10 power minus 3, which we have covered in the last class. And 10 power minus 6 to minus 11, what are the concepts? Absence of oxidation, that is associated with high vacuum technology, and also low molecular density, and time to form monolayer will be still longer and longer, and very long mean free path, which is very important in particle accelerators, because your particle is not getting hit by anybody. Longer the mean free path means what? It will not hit anybody. That is ideal, so that your electric and magnetic fields are good enough to accelerate continuously for your nuclear fusion and fusion applications. If you go to BARC, there is a vacuum division. If you go to ISRO, there is a vacuum division. Why? Because it is the vacuum technology. If you go to electronic industries, BEL, any other electronic industries in India, you will find lots and lots of high vacuum, ultra high vacuum. Production of vacuum we will see in the next section, but demand for high and ultra high vacuum is increasing like anything. There are two types of manufacturers in vacuum pumps, up to 10 power minus 3 rotary, roots blower, etc. And minus 3 onwards diffusion, turbo, ion, cryo, they will be different level of vacuum. So, technologies are equally challenging in both the places. For example, even in low and medium, it is not just only the value of vacuum, it is a dryness. For example, of late last 15-20 years, the dry pumps like screw pump, roots blower of course is there earlier also, now also it is getting more and more popular as a booster. and claw pumps and scroll pumps, they are becoming very popular. But earlier rotary pumps and piston pumps were doing the same duty. In fact, they are even having longer, higher pumping capacities. But what we require is quality, it should be dry. So, things are changing depending on the application. Why I am discussing pumps here is, depending on the application, it is not only the quantity of vacuum that is important, the quality of vacuum is also equally important. In metallurgical application, if there are two chambers, one is a 10 power minus 6, other is 10 power minus 7, a metallurgy professor will prefer a chamber where oxygen is less. So, if you have 10 power minus 6 millibar with a partial pressure of oxygen of 10 power minus 10, other side 10 power minus 7, but it is full of only oxygen, definitely for metallurgical process, metallurgist will prefer even this 10 power minus 6, because it is relatively more inert. So, metallurgically it will be pure alloys will come out of it, pure semiconductors will come out of it. So, semiconductor manufacturing is also coming up in a big way in our country. It requires a lot of pure vacuum, not only vacuum, pure vacuum. And when it comes to ultra high vacuum, one more point I would like to mention here, right here, is the history in which you bring the vacuum is very important. It is not just I want 10 power minus 10 tar, I use this ultra high vacuum pump, because the chamber was starting from atmosphere. So, initially these pumps are not useful for that 1000 millibar to 10 power minus 3, you use some other pumps. But selection of that pump should be dry pump, because same 10 power minus 3, these high vacuum pumps are going to take over, because normal pumps cannot pump below that. So, while taking over, it demands good quality. The 10 power minus 3 tar, which is the starting point of this ultra high vacuum pump, should be oil free. So, you should not have lubrication in the pumps used in the history of evacuation from 1000 to 10 power minus 3. It should not have water vapor. So, things like that. So, dry pumps are becoming very popular nowadays, partly because of a lot of research going on in biotechnology and pharmaceutical sectors and high-tech chemical engineering, partly because ultra high vacuum technologies also require initially pre-evacuation by dry pumps. 99.999% has been removed, but the remaining 0.01 contains oxygen or inert gases. Should I have a purging or not? So, these issues a designer has to take into account, keeping vacuum fundamentals in mind. So, high and ultra high vacuum, what you need to concentrate here is low molecular density, time to form monolayer, and oxidation reduction, and long mean free path. And it should be less degassing from the chambers. Chamber also should be properly designed. Ultra high vacuum is not just producing that level of vacuum. The way you make chambers, the way you select the pumps, the way you select the sequence of operation of the pumps, the way you detect the leaks, and there are certain applications where this ultra high vacuum has to be maintained in a sealed condition, like vacuum interrupters which are connected in the high voltage transmission lines in the power grid. Similarly, X-ray tubes which are there in the hospital for years together, and the TV tubes or the TV display systems, etc., even cell phones, they have to maintain the level of vacuum. There are certain applications where you have to maintain the level of vacuum continuously for years together. There are certain applications where only during process time you require a high vacuum. Once process is done, then it comes to the room temperature and normal affairs and all. Like in cell phone, we require during manufacturing high vacuum conditions, the semiconductor manufacturing, circuit manufacturing, or even chip manufacturing. Once it is made, they are available, you can keep it in moist atmosphere. Of course, you should be a little careful so that moisture is not there, etc. So, you should know ultra high vacuum applications, certain applications require during the process evacuation like particle accelerators, etc. When you are accelerating particles, you require very ultra high vacuum. When your experiment is over, you can keep it with a normal 10 power minus 6 star, nothing will happen. But X-ray tubes, no. TV tubes, no. You have to maintain vacuum interrupters, 20 years it has to be there on high voltage transmission line, a 10 power minus 8 star, waiting for a fault to occur. It will immediately open it as a fault current limiter. So, a reliability of sealed vacuum tubes is very high in ultra high vacuum conditions. So, the type of materials that you will be using is also equally important. All these concepts you have to think while you are discussing applications. Of course, each application we will take it up later, but right here in the concepts point of view related to applications, I wanted you to understand that long mean free path concept which we discussed in the class 2, how it is related now to application. Similarly, low molecular density and high electrical insulation, low degassing and absence of oxidation. These things you have to think again and again. Vacuum technology looks very simple like thermodynamics, but when you go into the deep depth, lots and lots of concepts come from materials point of view, process point of view, pumps point of view, measurements point of view, controls point of view, precautions to point of view, and also troubleshooting point of view. Downtime should be less in an industrial atmosphere. You cannot purchase a everyday pump. So, you have to maintain things properly. All that we will see in the production, measurement, troubleshooting, system design applications later. But right here, I want you to keep a note of it. In applications, you have to minimize the budget for the pumps and gauges and chambers and components, so that your profit will be more even in high tech industry. So, what are these applications? There are simple applications like induction furnace, for example, vacuum melting, casting, etc. In our IIT, we have several furnaces like that. If you go to defense laboratory in Hyderabad, there are lots and lots of very, very large scale furnaces. You can go there and see. Similarly, Midhani, you can go and see. Even DAE organizations, anywhere you go, you will find lots and lots of vacuum furnaces. Of course, nowadays electron beam melting, electron beam welding units are coming. All these metallurgical processes. Similarly, sintering and heat treatment, annealing furnaces that you see in the second figure. These are all metallurgical processes where you are melting, casting, heat treating, forming, etc. Once it is available is an ingot form or something, then comes the machining and the atmospheric pressure you can do, and this is mechanical engineering. But here metallurgical process conditions are always done at 10 power minus 6 star base vacuum or minus 7 star, and during process time, of course, the actual material when it is melting, its own vapors will come, which have to be continuously removed with a high throughput pumps. So, during process, vapors may come and spoil the vacuum level, but it is not spoiling, it is only the increase in pressure. But background vacuum should be 10 power minus 6 millibar, otherwise impurities will be there which will interact with this melt and then spoil the mechanical, thermal, various other properties which are related to microstructure of these metals and alloys. So, vacuum metallurgy is a big field, there are quite a good number of books available. Even in the engineering coatings, that is also basically vacuum metallurgy. Even the silicon manufacturing, it is a silicon is also a type of metal. So, manufacturing starts from metallurgy and material science, then goes to controls and electrical engineering and other chemical, other aspects will come into picture. So, processing of metallurgical applications is always done under high vacuum. You cannot do it at 10 power minus 2 minus 3, though 99.99% is removed, because a lot of oxygen will be there, and mean free path is not very long. It is maybe 20-30 centimeters at 10 power minus 2, whereas when you are trying to deposit a film of very high quality 2-dimensional film, which is the starting point of electronic circuit manufacturing, etc. The deposition should be done in a controlled manner. So, molecule should travel straight path, molecular beam epitaxy for example. it is having vacuum level of 10 power minus 10 torr, then only you will get the particles which are coming out travel in a straight path, and you can control them to control the thicknesses at micron level, submicron level, even angstrom level. The deposition rate should be 3 angstroms. So, such applications require high vacuum. So, in metallurgy, it is the materials processing under high vacuum to have proper structural things and minimum impurities and very good mechanical or thermal or other properties which are required for a particular application for which these metallic alloys are used, things like that. So, this is the induction furnace that we are seeing here. There is a cup, ceramic cup having all those materials which will be melted. There will be thermocouples to measure the temperatures. There will be alloy addition from the top, and entire thing is evacuated, and the entire cup can be tilted and then poured into a casting. Like that, several procedures can be done within the vacuum conditions. And how do you melt it? Electrical methods. You can pass a very high current, or you can also pass induction melting curves, induction melting. Here it is electrical thermal heating, that is sintering. Thin film deposition, just now I discussed, either you can physically evaporate it from a high current driven boat, and these material from the solid to liquid it will form here, from the liquid vapor will form, these molecules will go straight like beams, get deposited on a substrate. This is called thin film deposition. Almost every university, every institute will have this type of units in their physics, material science and metallurgy departments, even electronics department. This is physical vapor deposition. And very high melting point type of materials are some special situations. People try to use sputtering methods, where you do not physically melt it, you scratch atom by atom either by using DC voltage or RF voltage, but everything will be under vacuum conditions. So, the sputtering and physical vapor deposition, thin film deposition units, which are starting point of electronic manufacturing, based on which finally you will make these vacuum based gadgets like cell phone or laptops, etc., in the display systems, etc. You will end up in this type of deposition systems several times. Similarly, cathode ray tubes, which are used earlier in the monitors as well as oscilloscopes, even now for high current rating or high rated transmission tubes, etc., for electromagnetic waves, and still we use lot of bulbs. In fact, BEL is very famous in our country. They manufacture varieties of large quality pumps which are evacuated and sealed at 10 power minus 8 torr, etc., which are important as triodes and diodes or various types of things are used to make a high power electronics. Solid state electronics is only low power electronics. For high power electronics, you still use diodes. So, in such applications where a cathode beam, which is nothing but a cathode ray, which is nothing but a beam of electrons emitted from a thermionic filament and go in a straight path, create scintillations on a fluorescent screen, they are utilized to create images of different kinds. Of course, nowadays LED, LCD came, all these things, but there also between two layers, how do you keep those materials, etc., unless you evacuate and fill it properly, you will not be able to get proper quality, proper beauty of that display. So, everywhere vacuum is very important. And thermal insulation, for example, cryogenic containers, which are very important in cryogenic rocket engine, etc., where we have to store huge amounts of liquid hydrogen or liquid oxygen as fuel and oxidizer. Later they will be transferred into the rocket engine, and that we will discuss also in cryogenic applications in detail in the last session of these things. Right now, I am just trying to introduce high vacuum applications. Then I also already told you in thin film depositions, see how beautiful setup looks like, that way that you make the surfaces, inner surface of ultra high vacuum system should be optically finished. That we will discuss why at all, because the apparent area that you see is not 2 pi r h, it will be 1000 times more, because there are lots of up and down. So, if you finish it more and more like submicron finish, it will be better. And if you do not finish, lot of degassing will come, which will interfere with your vacuum conditions, and you will not get your proper film. There will not be electronics, there will not be space technology and nuclear. So, the processing of chamber technology is also very important in molecular beam epitaxy unit. This we will again discuss in thin film depositions and coatings when we go for applications. And you will find almost every material scientist or metallurgist or any biotechnology, everybody will be using scanning electron microscope, X-ray fluorescence spectroscope, to know the chemistry and physics and topology of it and surface smoothness, etc. All of them will be working under ultra high vacuum environment, because electron beam has to be accelerated by these electric and magnetic fields and arrive at the samples and produce diffraction patterns. It is not possible unless you have a background vacuum which is 10 power minus 8 to minus 9 tar, because beam will be lost. Okay. We will discuss these things later in analytical instruments. Interrupter I have already discussed. This is high voltage interrupter in electrical engineering application. Very good vacuum interrupters are being developed even in our India and also in abroad. Lots and lots of new developments are going on in these high voltage interrupters. The ratings are increasing, still higher voltage, 1000 kV, still higher currents, 10 kiloamperes like that. Similarly, X-ray tubes, long back, 100 years back they have started. Unless you have ultra high vacuum, the electron beam that is coming from the hot filament hitting the target area and producing X-rays. This we have studied in class 12 modern physics, how X-rays are produced, etc. So, I am not going to discuss. So, you will get X-rays when suddenly an electron beam is stopped on a target material and internal excitations in the atomic level finally will produce X-rays. Such seal tubes are heavily used everywhere in industry, medical and metallurgy and various applications. X-rays are used almost everywhere. Then it comes to space simulation chambers. You have to simulate how your satellite is behaving at 10 power minus 10 tar geostationary. You have to simulate how the space shuttle is going up and up during the initial takeoff. What will be the acceleration, how do you tilt it, or how do you do all this maneuvering using various gas bottles and various pneumatic techniques or various other techniques in the guided way. You cannot do it unless you understand how these shuttles are, how these satellites are behaving under these vacuum conditions. So, such huge chambers, if you find, you will see these are human beings. So, this chamber height is very high. It is almost like a 2-floor building type of thing with a main door, and it is being evacuated to 10 power minus 8 minus 9 tar depending on the mission. If it is a moon mission type of thing, you have to simulate up to 10 power minus 8 minus 9. If it is only polar satellite, etc., minus 5 minus 6. So, depending on those things, you have to simulate various things, space simulation chambers, where all the components which are qualified for space application are tested, and in whole satellite itself or shuttle itself can be tested inside these chambers. You can imagine how many thousands of vacuum pumps are used, how reliable the measurement should be, what should be the smoothness with which you are trying to make the internal surfaces. All that is very important. Similarly, when you come to the thermonuclear experimental reactor, which is going to be future of energy sources, by creating a sun on the earth, whatever reactions that go on tritium and deuterium mixing to produce helium and a high energetic neutron, and like that millions of degrees of centigrade is there in the sun. Then that produces a lot of energy. If you want to do it on the earth, that means you want to create a mini sun on every city. It is a controlled thermonuclear experimental reactor simulating the sun conditions. If you can do it, then we will not have energy problem at all. For it to happen, we have to produce million degrees centigrade. It is not possible unless you have a vacuum, unless you have an electromagnetic bottle. No normal material bottle can handle such high temperatures. We will discuss these things when you go to the nuclear application in detail, how superconducting magnets and electric fields, ultra high vacuum chambers, all these technologies together will create a international project which is funded by 7 countries. Right now, this is one of the very popular project where India is also involved in it. ITER, it is popularly known as. IPR looks after all these activities. Similarly, another very big nuclear activity, that is Large Hadron Collider. I would say this is the costliest experiment ever done on Earth. It is a very huge 27 kilometer type of diameter, that is nearly all the entire length of total length, as it is been mentioned in the articles, nearly 70 to 80 kilometers of length of these things and fairly good diameter. Such tubes are evacuated to 10 power minus 10 torr, where the beams are accelerated, whatever beam you want, Large Hadron Colliders, to simulate Big Bang, etc. And it is not possible unless you accelerate it by electric field without any collision from the other particles, so that no deceleration takes place, unless you deflect it with strong magnets which are superconducting. The superconducting magnets in turn require cryogenic conditions, they require vacuum. So, you require thermal vacuum to maintain various associated accessories. You also require beam vacuum, which is ultra high vacuum. So, both high and ultra high vacuum are required in Large Hadron Colliders. So, whether it is a nuclear sector or a space technology or an electron beam technology, which is required for most of the semiconducting devices with which we can make laptops and cell phones, etc. And semiconductor industry is a big industry by itself, and analytical instruments which are required at every stage of advanced technologies to understand the surfaces and interfaces, very high vacuum interrupters and very high vacuum X-ray tubes for medical and metallurgical applications. All of them utilize ultra high vacuum. They utilize long mean free path, because mean free path is so scattering is less. They utilize long mean free path, so that distance between the source and the substrate is less, so you will get pure films. They utilize no collision at all, so that electron beam will all the way travel and get diffracted to produce meaningful patterns, etc., etc. Okay. So, all the concepts and associated high voltage applications, high vacuum applications you have understood in this lecture. Okay. Thank you very much.